So, we will be beginning with a new module today, compaction, and it will be including the consolidation part also. So, before we enter into this section, we will be discussing one numerical that was remaining of the previous module, that is the seepage and the flow net. So, first we will move on to that and then to the next unit. So, see here this numerical, here you have to calculate the seepage through an other dam having the following given data. What are the given data? The coefficient of permeability in x direction is 8 into 10 to the power minus 7 meter per second, and in y direction it is 2 into 10 to the power minus 7 per meter per second. Now, the height of the dam is given as 60 meters. We will be seeing what is this. Freeboard is 2.5 meter, that is the water level is at what difference. Then upstream slope is given as this 2.75 horizontal is to 1 vertical, and downstream slope is slightly different, it is 2.50 horizontal is to 1 vertical. So, these two things are there, the coefficient of permeabilities are given to you, and then the crest width is 8 meters, and the length of the drainage blanket is given as 120 meters. So, for the very first thing we have to calculate the seepage. When we talk about the seepage, it is what? Q. So, it can be given as K into S. Because it is a non-isotropic medium, as you can see that coefficient of permeability in x and y direction are different. As these are different, so it comes out to be K should be something effective stress. So, K should be nothing but the effective permeability. It is not effective stress, it is coefficient of permeability, that is the effective value, equivalent value. So, this K dash can be found out by root of Kx into Ky. So, we found out the equivalent coefficient of permeability as this by applying this formula, K dash is equal to root of Kx into Ky. Now, when we see the diagram, what was given to you? The crest width was given to you, this is the crest width. Now, this is the entire embankment, this A point, see the boundary surfaces here, this E point, this J point and this H point C. This is the embankment, this entire portion is the embankment. So, here you have seen this is the embankment, and now see this is the length L that we discussed, and the parabola, the line which was there, it extends to 0.3 times of L. So, the remaining portion, this CD portion and parallel to this line A dash D dash portion can be equal to 0.7 times L. So, see here first we will be calculating the value of this AD dash, that is equal to 0.7 times CB. CB what we took in the diagram, it was taken as L. Now, tan theta 1, what is there? See, the slope is given to you, that this slope is 1 vertical is to 2.75 horizontal, and for the downstream side the slope is given as 2.5 horizontal is to 1 vertical. Also, one more important thing, the total height of the embankment was given as 60 meters, and the freeboard, that is the freeboard was given as 2.5 meters, that is this much was the amount of space available. So, the actual height will be 57.5 meters, that is the height of water that is behind the reservoir, that is inside the reservoir behind the embankment. Okay, now understand one thing, that there is no water level here, so that is at this. So, the difference for the flow to occur, there is a head difference. So, at this side the head is 57.5 meters of water, and at this side it is 0. Let us say if this is the datum, then the head difference is 57.5 meters. So, we can take the head difference to be 57.5 meters, that we will be considering. Now, understand that tan theta 1 we will be finding out what is AD dash, that is this length, what is this length here. So, that is equal to 0.7 times CB, tan theta 1 is equal to 1 upon 2.75, that you know by the slope, that is equal to CA upon CB. Now, CB you know that is 2.75 into the height by the triangle that we considered there, then CB comes out to be 158 meters, and this length CB will be taken into account here. So, AD dash comes out to be 110.6 meters, that we will be looking on later. Now, you have to find out that what is this length D, because A, the total distance from A to this H should be known to you. this drainage blanket length has been given as 120 meters. So, it is known, you have found out this thing 110.6 meters A dash D dash AD dash sorry, and this D portion, what is this D portion here? Now, we will be calculating this thing. Also see, this is the water level, this has been extended here, these are certain points E, J, E dash, J dash, E double dash and J double dash. This is the focus of the parabola, that is the top phreatic line. This is the top phreatic line, top flow line. So, this is the focus, and the directrix will be passing from somewhat this area, this length. Okay. Now, moving on now. So, to find out AH, let us see what is AH. In the figure, see, this point is A and this point is H. So, I told you that you have already found out this AD dash, you know this thing. Now, this FH is known to you, that is 120 meters, but we are breaking it into 3 terms, AE double dash, E double dash J dash and J double dash H. So, see this thing, A to E double dash, this one, this thing. Then we talk about E double dash to J dash, this thing. This is what you can easily find out, this thing, E double dash J dash as what, 8 meters. Now, from J double dash to H, so that is the third. So, this is easily 8 meters, you can easily say this. Now, for the first thing, AE double dash. Now, see AE double dash, you can see that this is the slope, 2.75 horizontal is to 1 vertical. So, you can simply apply the triangle tan theta formula in this figure and can simplify, and so the value of AE dash comes out to be 165 meters. Now, for J double dash H, it is on the downstream side. When you are talking about the downstream side, what happens? There is this slope, and the triangle that you will be considering is this triangle. So, this is the triangle that you will be considering. So, what is this length that you want to know out? That is the J double dash H. So, see here, we will again apply the tan theta formula, because we know 1 upon 2.5 is tan theta, that is one value given to us, and by the figure we can say that J double dash and upon J double dash H is nothing but tan theta 2. So, it comes out to be 2.5 into 60. So, J double dash comes out to be 150 meters. Now, when we have got these 3 terms, this comes out to be 150, AE double dash comes out to be 165. So, you get what? Total this AH length. So, you get the total length of AH, that comes out to be 323 meters. Now, you have to find out this value. You have found out the total thing now. Okay, the total thing is known to you now from this to this point, but you have not still yet found this D value. So, how we will be seeing this? We will be simply subtracting the known unknown portions and the known portions from this entire length. So, D comes out to be AH, that is the total length there, minus AD dash. AD dash, you can see this 0.7 times CB that you had already calculated in the very first step there, then FH minus FH. So, F is there, this, and then H, you know what is this? This is the drainage blanket length, 120 meters. So, when you subtract it, D comes out to be 92.4 meters. Now, when you have to calculate this Q is equal to this seepage, that is the Q value. So, it is K dash into S. Now, K dash you have calculated, that is the equivalent coefficient of permeability. Now, S is the value that is the that we have considered in the flow net. When we were discussing the flow net, at that time we took out the S value, that is the distance between the focus and the this directrix here. So, this is the focus of the parabola, and this here is the directrix. So, this portion is what? S. So, this S gives the discharge here, K dash into S. So, how to find out this S? That is equal to root of D square plus H square minus of small d, that is you have found out here this thing 92.4 meters here. So, when you put out the values, S comes out to be 16.4 meters. So, for finding out the discharge, you simply multiply the equivalent coefficient of permeability with the S value. So, it comes out to be 65.7 into 10 to the power of minus 7 meter cube per meter per second, that is the discharge. So, you have calculated the seepage here. Now, we will move on to the next module with this. So, see here we will be studying two topics, that is the compaction and consolidation. In the compaction we will be seeing what is the definition first of all, and then what are the different compaction curves, and the next topic will be the relationship between the water content and dry unit weight. After that we will be seeing what are the factors which affect the compaction, and also the field compaction equipment, and how do you control the compaction in the field, and the Proctor needle method. So, when we complete this compaction portion we will move on to the next thing, that is the consolidation, where we will be discussing the primary and secondary consolidation, Terzaghis 1D theory of consolidation, the consolidation test that is being performed there, and then the different type of soils, that is the normal and over consolidated soils. Then the over consolidation ratio, what is it, we will be discussing that thing also, and then we will move on to the determination of coefficient of consolidation, that we have already studied in the permeability topic, but it was a very small aspect that we saw there, but now we will be studying this in detail. So, moving on with the next, the very first topic in this module, the soil compaction. So, understand one thing, that many a times soil itself is used as a construction material, but in the construction of engineering structures such as highway embankments or earth dams, loose fills are required to be compacted, because when you you are, let us say you are taking a you want some soil here, you have some soil in some burrow pit, let us say it is a pit, there is some soil here. Now, you want to construct an embankment. Now, when you want to construct this embankment where the water is to be stored here, and let us say water is also at the downstream face also. So, when this is the case, so what happens here, that this embankment should be very much strong. If the soil itself is used as a embankment material, so it has to be properly compacted. So, the loose soil from this pit is brought to this site where the embankment is to be constructed, and it is being compacted, being acted upon by some force. So, what is this force, and what are the different methods to consolidate into a solid mass, that we will be seeing here. So, basic thing is why these loose fills are required to be compacted. It is to increase the soil density and to improve their strength characteristics. So, see here this thing, this soil pit, the soil in this burrow pit, what happened, it was in a very loose state, it was not a compacted one, it was having some very much less strength value. But when you talk about this embankment, what happened here, when we compacted this thing, it is a very much strong, its characteristic is in terms of shear strength or in terms of bearing capacity, it will be much improved one. So, compaction can also be said to be an important method of a soil improvement. Now, let us look what is compaction basically. Compaction is the process in which soil particles are artificially rearranged. Okay, important thing, see soil process and then artificially rearranged. Artificially, that means it is not a natural process, that is we have to do this. Okay, how we have to do this, we will be seeing this. So, see, artificially rearranged and packed together into a closer state of contact, Obviously, when you are trying to compact something, what happens, they will move into something more, into a much more closer state by mechanical means. The third important thing here, by mechanical means. So, you are using some extra effort or some different equipments here in order to modify its engineering properties. So, you will be modifying the properties, that we will be seeing what happens there. Now, compactness of the soil is measured in terms of its dry unit weight, that is the gamma d, that you had already studied in the first chapter. What is the gamma d and what are the different relations there, that you had already discussed. Now, see what happens when you compact a soil, the void ratio, that is the volume of voids with respect to volume of solids, the voids will be reducing because you have compacted the soil. The soil which was this much there, now it has been compacted to a much smaller volume. So, the void ratio will be decreased. So, E decreases. Now, the permeability, because the soil is more compacted, so what happens there, the voids which have been allowing the passage of water, that has now been reduced. So, the permeability also what? It reduces. But what happens to the denseness? When you compact loose fill, what happens? It is brought to a smaller volume. So, in that case the denseness will increase. So, the denseness value increases. And what happens to the shear strength? Shear strength will also increase. We will be discussing this in the fourth module, shear strength. And the bearing strength, that is the holding capacity for the soil to hold any structure, that is the bearing capacity will also increase, and so will be the stability of the soil. Now, how to achieve this compaction? So, you have known this thing, that is the process, it is artificially rearranged, and then third is the mechanical. So, what are the different mechanical processes? Now, see, in the field it is achieved by vibrators, rollers, tampers, rammers and vibroflotation technique. So, we will be studying it in detail, these all the compaction equipments that have to be used. Now, the very first thing here, that what is the difference between compaction and consolidation? So, the term looks almost similar, but there is a very much big difference. In compaction, we go on with the definition first. It is a mechanical process, the very first thing, which is carried out instantaneously, in which the volume of soil is reduced. Okay, this thing, remember this point here, due to the expulsion of air. So, the cause of volume reduction is the expulsion of air from the voids of the soil. So, you know already that what does the soil comprise of? Soil comprises of the solids, and what happens then? It contains the water, and then what is there? Air. So, if you are trying to compact soil, what happens? The air is expelled out, and the volume of the soil that was initially, let us say V, it will somewhat reduced, it will somewhat get reduced. Now, see the second thing here, the consolidation. It is a natural process which takes place gradually. Okay, this important thing, gradually, that we will be seeing, in which the volume of the soil is reduced due to expulsion of water from the voids of the soil. So, here the volume reduction is taking place, but what happens there? The reason is the expulsion of water. Now, another important thing, that for compaction the saturation value is less than 1, that is saturation is less than 1. Why? You can also think about it, because when the saturation is less than 1, that means what? There is in the voids there is water also present and also the air present. So, these two things are there in the voids, but in case if the S value tends to 1 or becomes 1, what happens there? All the air has been expelled out. So, now we will move on to the consolidation part. So, when all the air is expelled out, what happens? Voids contain only and only water, and voids contain only and only water. So, at that point of time the consolidation process will begin. So, see here, when we talk about this compaction part, let us say if this is the volume V1, initial volume V1, before the compaction of soil, it had some solids, it had some water and it had some air. Now, when we compacted this soil, compaction is what? A mechanical process, and wherein you compact the soil and the volume of soil is reduced by the expulsion of air. So, the air has been expelled out, so air's volume will be reduced. So, let us say this much air has been expelled out. So, the new volume of air will be only this portion, and the total volume that was V1 here, it has been reduced to V2. So, this second part is after compaction here. Now, let us see what is the consolidation. See here, if the initial volume is say V1, that was earlier also the case. Now, there is solid, water and air. What happens then in case of this second one, when the consolidation is taking place, what happens here? That let us say we are removing this thing, air, we are having solid and water only. So, see this thing, that when the volume is reduced, when the consolidation takes place, the volume is reduced. So, the volume is reduced and the volume comes out to be V2, that is due to what? Water is coming out. So, in this case, in the second case, the air is not the factor, but the water is the factor here, water comes out. But in the compaction portion, what was there? It was the air that was the governing criteria. So, in this thing, the entire thing is water. The value of saturation is 1. When you talk about this value of saturation, that is 1, so at that time there is no air. So, we will not consider the air here, it is only the water and the soil solids. Now, when you talk about the laboratory test, what happens in this? It was first of all this compaction laboratory tests were determined in the 1930s by R. Proctor, and he also devised a test for this thing. The compaction characteristics and the degree of compaction are obtained from the lab tests. Now, in these tests a specified amount of compactive effort, okay, a specified amount of compactive effort. What is this compactive effort? We will see, is applied to a constant volume of a soil mass. This compactive energy is reported in terms of kilogram force meter per meter cube, or in SI units as joule per meter cube. So, this is the compactive effort. So, we will see how it happens. In lab mostly impact compaction is used, that you will be using some impact force there. In field, when we talk about what happens, compactive effort is the number of passes of a roller on the soil. That is, if the you would have seen multiple times on the when you were a kid, that the road is being prepared, or at this stage also of your life, you would have seen that when a road is being constructed, what is there? The first thing is the compaction. So, compaction is taking place with the help of a roller. Now, see this very important 4 tests here. So, the very first thing here, the standard Proctor test. This standard Proctor test was devised by Mr. R. Proctor. Later on, Indian standard light Proctor test was devised by India, and then this modified Proctor test was developed during the World War I, when it was required for the heavy landing of the jets and aeroplanes there. So, modified Proctor test included more compaction of the soil. So, on this basis the IS standard, Indian standard modified Proctor test was also defined. So, what happens there? There is some mold here, let us say this is the mold, and there is some soil which is there. Now, we take this soil here and we put it in the mold in layers. We took the first layer and then we compact it by some rammer, we compact it, then we scrape the surface, and then what happens? Then this is the first thing, and then we put another layer of soil, let us say this, and we compact it, then we scrape the surface. Why do we scrape the surface? Because when you scrape the surface, what happens? The next layer which you put in will be homogeneous and not stratified. Otherwise, if you do not scrape the surface, the soil will be stratified soil. So, in the third layer you will be also again putting some soil and then compacting it. So, this is how the mold is taken up and then the compaction process is applied. So, understand here one thing, what is the volume of mold? The volume of mold taken in the standard Proctor test and the modified Proctor test are same, that is the 944 ml, and that can be given as 1/30 feet cube. When you talk about this IS light Proctor test, the volume of mold used for Indian standard is 1000 ml. See here, both the test it is 1000 ml. When we talk about the rammer weight, that is the rammer this you used here, this rammer's weight has also been specified in the code, that is when we talk about the standard Proctor, it is 5.5 lbs, that is 2.495 kgs, and Indian conditions it has been modified to 2.6 kgs. When we talk about the heavy Proctor test or the modified Proctor test, it is the weight has been almost doubled, 5.5 lbs to it has come to 10 lbs, that is 4.54 kgs, and for Indian conditions it has been specified as 4.9 kgs. Now, what happens, like I have shown you in this figure, that first layer is there, then you compact it, and then you put the second layer, and then you compact it, and then you put the third layer. So, this is a very simple process for these light Proctor tests. So, here the 3 layers are provided, and for each layer the compaction here the 25 number of blows are given. So, in Indian standard light Proctor test also 3 layers at 25 blows each, and when we talk about the heavy test, modified Proctor test, heavy test here, so here 5 layers are there and at the rate of 25 blows each layer. So you are giving what, 125 blows in the modified Proctor test, and when you talk about the Indian standard, what happens there, it is almost the same, it is also the same here, 5 layers at 25 blows each. Now this rammer has to be imparted from a height. When you take a soil here and rammer is like trying to, if you leave it, what will be there, some energy will be imparted to the soil. So this height is the free fall height of the rammer, that in the case of standard Proctor test is 12 inches, that is 304.8 mm. When we talk about Indian standard test, it is 310 mm, and then when we talk about this thing, the modified Proctor test, it is 18 inches, that is 457.2 mm, and for the IS modified Proctor test, it is equal to 450 mm. So you have to remember these values, and you can directly apply and get the compactive effort values, and what is the compactive energy there, and so we will be looking on now. Now after you have used the mold and compacted by this process that we have already discussed, now the sample of the soil compacted in the mold is collected and tested for the water content. So you have compacted the soil first of all in the mold there, so you have got, let us say, 3 layers, and you have compacted it now. So what happens after compaction, you take the soil sample and test the water content. This water content is used to find out the dry unit weight, because gamma d is equal to gamma by 1 plus w. So you know this unit weight, and unit weight can be found out by practical experiments. Now you know the water content. So what happens, gamma d value, why you need to find out the gamma d value or the water content value, because water content will help in finding the gamma d, and this gamma can change, because let us say if there is rain, what happens, the value of this bulk unit weight will be changing to some other value, but the dry density of the soil will always remain the same. So the test will be repeated at different water contents, and the dry unit weight of the soil at each water content will be noted and will be represented in the form of a curve, that is the compaction curve, which we will be referring to in the next class. Thank you.